I bet you have wondered about PCIe lanes. You are building a PC, looking at those slots, seeing numbers like X16, X8, X4, and X1, and thinking, what do these even mean? It is a common point of confusion, even for experienced builders, and it is something that can genuinely impact your system's performance, especially if you are trying to push the limits with multiple high-end components. Let us really dive in and demystify this critical piece of PC architecture. Let me unpack PCIe lanes for you with a simple analogy. Imagine your computer's motherboard as a bustling city, and data as the cars needing to get around. PCIe lanes are like the individual roads or highways within that city. The more lanes a road has, the more cars' data can travel on it simultaneously, and the faster they can reach their destination. So, when we talk about X16, think of it as a 16-lane superhighway, while X1 is a single-lane road. At the core of this whole system is your CPU, the central processing unit. Think of the CPU as the primary train station or airport in our city. It is where most of the critical data originates and needs to go. Most modern CPUs come with a specific, fixed number of PCIe lanes built directly into them. These are the fastest and most direct lanes in your system, typically dedicated to your most demanding components. Building on that, not all components connect directly to the CPU. That is where the chipset comes in. This is often referred to as the Platform Controller Hub, or PCH. Imagine the chipset as a secondary, smaller train station or a major traffic control center within the city. It acts as a go-between, managing connections for many of your less bandwidth-hungry peripherals and routing their traffic efficiently. So, what exactly is a lane? A single PCIe lane is essentially a pair of differential signal wires for transmitting data and another pair for receiving data. It is a two-way street for information. When you see X1, that is one of these pairs for transmit and one for receive. When you see X16, it is 16 of these pairs working in parallel, significantly multiplying the available data bandwidth. The key is understanding that these X numbers refer to the number of electrical lanes a slot provides. A PCIe X116 slot physically has the pins for 16 lanes. An X8 slot has pins for 8, and so on. This physical configuration dictates the maximum potential bandwidth the device can utilize if plugged into that slot, assuming the electrical connections are all active. The more lanes a device can use, the higher the potential bandwidth, meaning more data can move between the component and the CPU or chipset per second. Think of it like a wider internet connection. You can download more things simultaneously or download larger things faster. This is crucial for components that constantly shuttle massive amounts of data, like high-end graphics cards or NVMe SSDs. What is fascinating is how these lanes have evolved through different PCIe generations. We have had 3.0, 4.0, and now even 6.0 in development. Each new generation doubles the bandwidth per lane compared to the previous one. So, a single PCIe 4.0 lane is as fast as two PCIe 3.0 lanes. This means a PCIe 4.0 X8 slot has roughly the same bandwidth as a PCIe 3.0 X116 slot. This leads to a really important point. A physical X16 slot does not always mean it is electrically wired for all X16 lanes. Some motherboards might have a long X16 slot, but if you look at the specs, it might say X16 X8 electrical. This means even though the physical slot can fit a large X116 card, only 8 of those lanes are actually connected and active. It is like a 16-lane highway where half the lanes are closed for maintenance. Initially, your CPU's direct PCIe lanes are typically reserved for your graphics card, which is often the most bandwidth-hungry component. Most consumer CPUs offer 16 or 20 dedicated lanes for this. So, if you have one high-end GPU, it will likely take up all 16 of those lanes, operating at X116 speed. However, with the rise of incredibly fast NVMe SSDs, these storage devices also demand PCIe lanes. Many modern CPUs will offer an additional 4 direct PCIe lanes specifically for a primary NVMe SSD. This means your CPU might have 16 lanes for the GPU and 4 separate lanes for an M2 NVMe drive, totaling 20 CPU direct lanes. Taking it further, what happens when you start adding more components? Let us say you want to run 2 graphics cards, or maybe a GPU and multiple NVMe SSDs. This is where the limited number of CPU lanes becomes a puzzle. You only have so many direct superhighways from the CPU, and you need to allocate them wisely. This leads us to the concept of shared lanes. If your CPU has 16 lanes and you install 2 GPUs, the motherboard often has to split those 16 lanes. Instead of one GPU getting x16, each GPU might get x8. This is a common configuration for multi-GPU setups, ensuring both cards have a substantial, though not full, allocation. Now, let us talk about the chipset's lanes. The chipset itself does not just manage traffic, it also provides its own pool of PCIe lanes. These are generally used for your secondary M.2 slots, SATA ports, USB controllers, network interfaces, and other expansion cards. These lanes are usually slower in generation than the CPU's direct lanes, for example, PCIe 3.2.0 or 4.0, even if the CPU supports 5.0. So, when you install an NVMe SSD into a secondary M.2 slot, it is often drawing its lanes directly from the chipset, not the CPU. This is perfectly fine for most users, as the bandwidth provided by the chipset's lanes is still incredibly fast for storage, often more than enough for everyday tasks and even heavy gaming. And here is where it all comes together: SATA drives. Unlike NVMe SSDs, traditional SATA drives do not use PCIe lanes directly for their data transfer. Instead, they connect to the chipset, which then uses its own PCIe lanes to communicate with the CPU. So, while SATA does not consume your PCIe lanes, it relies on the chipset's overall capacity. The chipset itself needs a way to talk to the CPU, right? This connection is typically called the DMI link, or Direct Media Interface. This DMI link is essentially a dedicated set of PCIe lanes, usually X4, that acts as the primary data highway between the CPU and the chipset. All the traffic from the chipset's connected devices has to flow through this DMI link to reach the CPU. Here is the cool part: this DMI link can become a bottleneck. Imagine all the data from your secondary NVMe drives, USB devices, network card, and other peripherals trying to squeeze through that X4 DMI link simultaneously. For most typical use cases, it is perfectly adequate, but for extremely heavy workloads involving multiple high-speed devices, you might see a performance cap. Now let us talk about bifurcation. This term refers to the ability of a single physical PCIe slot, usually a CPU-connected X116 slot, to be electronically split into multiple smaller logical slots. For instance, a single X116 slot can be bifurcated into 2 X8 slots, 4 X4 slots, or even 1 X8 and 2 X4 slots. Bifurcation is a critical feature if you want to run multiple add-in cards that require significant bandwidth from the CPU's direct lanes. This is often seen in high-end workstations or servers where users might want to install 2 GPUs, or perhaps an ultra-fast PCIe RAID card alongside a powerful graphics card, all drawing directly from the CPU. Consider how this works in practice. If you have a motherboard with a primary X16 slot and a secondary X16 slot, often only the primary is truly X16 from the CPU. When you install a second GPU, the motherboard will automatically bifurcate the primary X16 slot into 2 X8 segments. This means both GPUs run at X8 speed, which is still very capable for most applications, especially with newer PCIe generations. Evolving from that, what if you have a GPU and then you want to add multiple NVMe SSDs directly to the CPU lanes, perhaps on an adapter card that houses several M.2 drives? You would need a motherboard that supports PCIe bifurcation on a CPU-connected slot, allowing you to split that X16 link into, say, 4 X4 links, 1 for your GPU and 3 for your M.2 drives. Motherboard manufacturers make crucial decisions about lane allocation. Some boards prioritize multiple GPU setups, providing more direct CPU lane options for PCIe slots. Others might prioritize storage, offering more M.2 slots connected directly to the CPU, even if it means fewer direct lanes for other expansion cards. This is why you will see motherboards with different PCIe slot configurations. One might have a 5x16 slot, 3x16, 3x16, 3x16 setup, while another has 5x16, 4x16. These numbers tell you the physical size, but the actual electrical lane allocation, e.g. x16xwux or x8xxx, is found in the manual and is dictated by the CPU and chipset capabilities. The ultimate insight is that lane constriction only truly matters when you are dealing with extremely high bandwidth components that are actively being pushed to their limits simultaneously. For most gamers with a single GPU, the difference between x16 and x8, especially on PCIe 4.0 or 5.0, is often negligible, sometimes only a few percentage points in frame rate. However, if you are a content creator rendering 8K video, running multiple professional-grade GPUs for compute tasks, or using several ultra-fast NVMe SSDs for video editing, then having sufficient PCIe lanes becomes absolutely critical. In these scenarios, every lane translates directly into performance, reducing bottlenecks and speeding up your workflow. When planning your build, consider your primary use case. If it is a gaming rig with one GPU and a single fast NVMe, you likely do not need to stress too much about extreme lane allocation. But if you are building a powerhouse for professional work, always check the motherboard's manual for its specific lane distribution and bifurcation options. Adding to that, the cost of motherboards often scales with their lane management capabilities. Boards designed for enthusiast or professional use, with advanced lane splitting and more direct CPU-connected M2 slots, tend to be more expensive. This is because they incorporate more complex PCB designs and often require additional components to manage the lane routing effectively. The future of PCIe is exciting. With PCIe 5.0 already here and PCIe 6.0 on the horizon, the bandwidth per lane continues to increase dramatically. This means that even fewer lanes can provide incredible performance, potentially making bottlenecks less common for many users and allowing even more powerful components in the future. The biggest lesson is that PCIe lanes are the nervous system of your PC, dictating how fast and efficiently data flows between your critical components. Understanding them allows you to make informed decisions when building or upgrading, ensuring your system is not bottlenecked by an invisible traffic jam.